we move on to this non-inverting amplifier. The non-inverting amplifier is looking like this. I know it's a little bit confusing. What's the difference between the previous one? We're going to talk about that later, so don't worry. But just focusing on this guy. Okay, so in order to find the relationship between your input source and the output, we do this 3-step, right? The ideal Opamp assumption with the feedback. We're going to use IN is 0 and V positive is same as V negative. That's the assumptions, right? And then what do? We do the KCL at the negative node. So we can define IS. This here is IN. We have feedback current. Let's call it IF. And KCL is, again, flow in, flow out. So we can have IS plus IF equals IN. And what's that IN? IN is 0 because we just assumed that, right? And the next step is what? We want to find out these I's. So IS is nothing but here to there, there's a current flow, right? So voltage at this point is what? It's 0 because it's at the ground. And that is flowing to negative, V negative, and it's divided by RS. And IF is what? V out and V negative. V out, from here you go to V negative across this resistor. So V out to V negative, that is divided by RF. Right? Then what do? We plug these back into this equation, right? So these are going in here. So it's negative V negative divided by RS plus RF V out minus V negative equal 0. Then we need to find out what this guy is, V negative. What's V negative? V negative and V positive in this case is going to be Vs, because Vs is same as V positive and V positive is same as V negative, right? So this is what I mentioned. This is the ideal assumption, and it's not going to be always 0 or Vs or anything. The actual value is going to change depending on whether V positive or negative is connected to a certain node. But this relationship, V positive is same as V negative, that is always going to be the same. Okay, so we can change this into RS Vs plus V out minus Vs RF equals 0, right? And after you do a little bit of math, you're going to get your output voltage is 1 plus RF over RS times Vs. So our output voltage, V out, at this point is 1 plus RF over RS times Vs. Okay? It's slightly different from what we had for the inverting amplifier, which was your output voltage is negative RF over RS times Vn. Okay? We have 1 plus that thing. So if we write some stuff down, gain is always positive and greater than 1. Output over input ratio, that's the gain, right? And this value here is what? It's always positive because RF and RS, those values are resistors. We always have positive values, right? So it's 1 plus some positive number. So it's always positive, and even it's always greater than 1. So that means, can we shrink down the input and have a small thing coming out into the output? No, because the ratio you multiply is always greater than 1, right? In order to make this thing smaller, you need to multiply 0.5 or 0.1 or something like that. But it's impossible to make a value that is less than 1. So your output is going to be always amplified or greater than your input signal amplitude. All right? That's this non-inverting amplifier. So the out amplitude is always greater than the input amplitude, something like this. So if we try a simple example, the one I actually just copied this whole thing down there, so it's just exactly same thing. RS was 1K, RF was 10K, and we had a same input sign, 50 hertz, and we would like to find out what's the V out. Then V out is 1 plus RF over RS times V in, right? So it's going to be 1 plus what? RF is 10K divided by 1K, right? And V in is what? 0.15 times sine 2 pi 50 t. By the way, t is time, right? And this k goes away. It's 10 over 1, so it's just 10. So it's 11 times 0.15 sine 100 pi t. And that is going to be 1 sine 100 pi t. All right? The waveform, if we had an input signal like this, it's a sine wave, and it had an amplitude of what? 0.15 volts. Then your output waveform should look like this. And the amplitude is what? It's 1.65. Amplitude here is negative 1.65 volt. All right? So it's not inverting. If it's positive, your output is positive. If your input is negative, your output is negative. You see? So it's not inverting. So it's a non-inverting amplifier. And it's just getting greater. And from the previous case, it was 1.5. In other words, this here is negative 1.5, and the amplitude here is 1.5 volt, right? And we saw that it's flipped over with 1.5. However, in this case, slightly different, 1.65, because it's 1 plus RF over RS, and it's in the same sign. If it's positive, your output is positive. If your input is negative, your output is negative. All right? So I wanted to keep these two together because they are really confusing. From here, let's just write down and summarize first, and then maybe I'll explain. So for the inverting amplifier, gain that is smaller than 1 is possible. But for non-inverting, gain always greater than 1. And it is said inverting amplifier is a little bit more stable. In other words, it has lower distortion, or it has a lower input impedance. And on the other hand, for non-inverting, it has a higher input impedance. So this is going to be used for impedance buffer or a voltage follower. If we take a look at the figure on the top, these two, the easiest way to identify which one is which is by looking at where your signal is being connected. So this guy is going to negative and this guy is going to the positive, right? Other than that, it's the same. It has a resistor, and that resistor is what? Connected to from your output to your input with a negative, right? So this, they're the same. The only difference is whether this is connected to your negative or whether instead of being here, whether it's there. All right. So if your signal is being connected to your negative input, then it is going to be the inverting amplifier. All right. A very simple way to kind of memorize, because your source is being inverted. And if your source or input is connected to the positive input, then there's no flipping over. It's like this, okay? So that's kind of simple way to tell whether this is an inverting or non-inverting amplifier. Of course, it needs to have a negative feedback, and generally it has a resistor connected, and generally in the output it has also a resistor. That way you can measure your V out, okay? And the major difference between these two is for an inverting amplifier, you can have a gain that is smaller than 1. In other words, you can shrink down your signal. If you had a 10-volt signal in your input, you can have 1 volt coming out or 2 volt coming out by selecting a gain value that is smaller than 1. However, for a non-inverting amplifier, your gain is always greater than 1 or equal to 1. So in other words, you cannot shrink down your signal, right? And generally speaking, these two have almost same stability. It's for example, in our lab, for inverting, non-inverting, you're going to have a beautiful signal coming out. However, in case you are hitting the limit of an op-amp also, well, in mathematically, right now we're just doing everything ideal, so it's just math. But if you really use a actual op-amp, it may have some limitations. Like it's going to have like a physical limit there, right? So if you are hitting the limit of a specific op-amp, say if the frequency is too high or the gain is super large, then it is said this guy is slightly more stable compared to the non-inverting, okay? However, if you're hitting the limit, just buy a better one. You know, that's kind of the first option you want to like try, and then, but still, if you have to live with this, maybe you go with this, all right? And the last piece of information, this guy has a high input impedance, and that is going to lead us to another concept, which we are going to talk down here, is a voltage follower or an input impedance buffer. And this is a special case of inverting, non-inverting amp, where RF is 0 and RS is infinite.